Okay, so today we're gonna do lecture 6. This is a new topic. In the previous 5 lectures, we covered kinematics in 1 dimension and 2 dimensions, and we covered vectors, which were the necessary tool to describe objects with magnitude and direction in more than 1 dimension. So today we're gonna use vectors again, but we're discussing forces and free body diagrams. Forces are what cause motion. So we're essentially looking at the other side of the equation. Previously, we looked at motion without considering its cause. Today, we're going to consider the cause itself. So the outline for today is as follows. So first, introduction, like a big picture view. Then we're going to address what is a force. And in that question, we're going to have 2 subsections. We have a characterization of forces, what all forces have in common, then visualizing forces. And this is where vectors come in handy. After that, we're going to mention many forces, get introduced to many forces. So it's a catalog of forces where we discuss about 6 forces. So weight or gravitational force, then spring force, tension force, normal force, friction, and drag. So these are the forces we're going to be dealing with throughout the semester or throughout the class. There are, of course, other forces, but we're not going to be concerned with these. There is electric force, there is magnetic force, there is nuclear force, but all of these we're not going to discuss in this class. With these forces at hand, we're going to learn how to draw a free body diagram. And finally, how to combine forces. Okay. In all of this, we don't discuss Newton's laws. We don't discuss how forces affect motion. So today we're mainly concerned with the forces themselves, how to define forces, how to introduce them, how to understand them without addressing what they do to motion. In the upcoming lectures, we're going to discuss Newton's laws and how these forces affect motion and how they cause acceleration and generate the kinematic equations that we saw before. But today, we're just going to introduce forces. Okay. So let's get started with the introduction. Previously, we discussed kinematics. And we said that kinematics is the study of motion without considering its cause. This is the important statement here, without considering its cause. Now we move to dynamics. Dynamics is the study of the cause of motion. Together, these two give rise to the science of mechanics, which is the study of motion in general. We're gonna just give a very brief overview of Newton's laws before discussing forces, just to get an overview of what we're gonna see ahead. So Newton's laws, these are 3 laws. So Newton's first law basically tells us that if an object is acted on by no forces at all, then this object will either remain at rest if it was at rest, or remain at motion if it was at motion. So Newton's first law, no force, no change of state. So rest remains at rest, and motion remains at motion. This is a non-trivial statement. Before Newton, it was widely believed since the times of Aristotle that objects tend to be at rest. If you leave an object long enough, it will tend to come to rest, even if it was moving. And that to move an object, you need to exert a force on it. What Newton's first law says is that no, if you didn't intervene, an object will remain at motion. It will not naturally come to rest if you leave it, even if you leave it forever. It will not come to rest. It will keep moving forever if you didn't intervene its motion. So this is non-trivial, although now we think of it as a trivial statement. That's just because we now understand how the world works a little bit better than Aristotle did. But this is the content of Newton's first law. Then Newton's second law, this tells us what forces do. What's the effect of a force? So this tells us basically that forces cause acceleration. It's not that forces cause motion. No, forces cause change in motion, change in velocity or acceleration. It's a cause and effect relationship. The force is the cause, and the acceleration is the effect. Okay? So if a net force acts on an object, it makes it accelerate. Then there is Newton's third law, which says that if we have two objects and one object exerts a force on the other, then the other object reacts by exerting a force on the first object with the same magnitude, but in the opposite direction. It's always concerning interaction scenarios. You always have to have two objects interacting for Newton's third law to make sense. Unmute yourself and tell me, because I don't want to be going off without you guys hearing. Okay, so let's get back to where we were. So Newton's third law, if we have two objects, object A and object B, object A exerts a force on object B denoted by F sub AB. Those subscripts are crucially important. We're going to use them a lot when we discuss Newton's third law. Then object B reacts. It exerts a force back on object A, which we denote by B on A. So Newton's third law tells you that the magnitudes of the forces are the same. So the magnitude of FAB is the same as FBA, but the direction is different. So FAB is negative FBA. So they point in opposite directions. The important part is that the action and reaction forces act on different objects. So if this is object A and this is object B, then we have action and reaction forces. So if I isolate A and say, okay, there is a force from B on A, and then I draw B by itself also isolated, then there would be FA on B to the other side, and it's acting on a different object. Okay? So this is a very brief view of Newton's laws of motion. We're going to discuss them in details in the next lecture. But notice that in all of this discussion, we didn't discuss in any detail what those forces are, what the nature of these forces is. So we're just talking generically about a force. We didn't say, is it a friction force? Is it a gravitational force? Is it a tension force? Is it an electric force? We didn't say anything about what this force is, okay? So what is a force? So intuitively, we think of a force as a push or a pull, which is a good enough starting point for now. So let's say how to characterize forces. So characterizing forces by features they have in common. So a force is a push or a pull. That's essentially how we think of a force. Another important feature is that a force acts on an object. Just bear with me with the definitions. I know some of these definitions might seem trivial, but we're gonna need the definitions just to be on a good, solid ground to discuss things meaningfully, instead of just having intuitive notions that might not be very accurate. So it's better to bear a little bit with the trivial definitions. So a force acts on an object. This just means forces don't exist in isolation. You have to have an object that receives the force. Even if you have the agent that does the force, if there is no receiver, then the force just doesn't occur. So forces don't exist in isolation. Then a force requires a specific identifiable agent. If you cannot, or if an agent cannot be identified, then the force probably doesn't exist. So for example, a freely falling ball experiences a gravitational force. In this case, the agent is the whole Earth. The Earth exerts a gravitational force on the ball, and it causes it to accelerate. So that's the agent. And the agent doesn't have to be a human being. It can be an inanimate object. A wall can exert the force, and it's the agent. A table can be the agent. But there has to be an agent. If there is no agent, there is no force. A force is a vector. This is very important. If you push an object, you can push it up or down, you can push it left or right, you can push it forward or backward, you can push it in any direction, which means it's not just how much force there is, but there is also in what direction the force is exerted. This is the very definition of a vector. So we characterize a force by a vector, and we give it the label F with an arrow on top, as usual. Then there is two big categories of forces. So a force can be either a contact force or a long-range force. Contact force, from the name, requires the two surfaces to be in contact. For example, friction force is a contact force. The agent and the object must be in contact. By contrast, a long-range force doesn't require the agent and object to be in contact, and the very famous example of that is gravity. A freely falling ball is receiving a force from the whole Earth, even though it's in the air, so there is no contact between the surface of the Earth and the ball, but still there is a gravitational force. So these are common characteristics shared by all forces, genetic features of a force. How do we visualize a force? We said a force is a vector. We learned how to visualize a vector. So because force is a vector, we draw it as an arrow with a label F. The tail of the arrow is at the object receiving the force. So this is the object. The length of the arrow is proportional to the magnitude of the force, and the direction of the arrow is in the direction of the force, just in the same way as we discussed vectors before. Also, just for simplicity, we denote objects by points. So this object could be a car, could be a table, it could be any complicated object, but usually in physics, we convert complex real-world situations into like simplified models. So even if this object is like, let's say, a car, and this car is being pulled by a rope, and it's pulling the car forward, then this whole car, I can just draw it as a point, and the rope is just a vector tension T. This would be how I describe this real world situation by an abstract picture. Good. Okay. So next, what we're gonna do is discuss a whole list of forces, because these forces are gonna come up later in different situations. So it's the catalog of forces we're going to next. So we give an overview of forces that we deal with here. So let's start with weight. We denote weight by the symbol W, which is not what I prefer, because later in the class we're going to denote work by W, or FG, which is the one I do prefer. Weight is the gravitational pull of the Earth on an object. So weight is a force. It's not measured in kilograms. Usually in everyday language, we talk about weight as mass, but in physics, we differentiate between these two different concepts. Weight is a force. It's measured in newtons, but masses are independent of forces. Mass measures how much an object resists motion, which we will discuss when we discuss Newton's second law. But mass is different from weight. Okay? The magnitude of the weight of an object is m times g. This is near the surface of the Earth. So m is the mass of the object, and g is the acceleration due to gravity near the surface of the Earth. As usual, g is positive 9.8 meters per second squared. Remember that g itself is the positive number, and if we want to denote direction, we put a negative sign in the acceleration, not in g. So this is the magnitude. If we said forces are vectors, so we can't just mention the magnitude and not direction. So direction of the weight is vertically downwards. This is towards the Earth. If we take the positive direction to be up, then the gravitational force as a vector is negative mg along y hat. Remember the unit vectors x hat and y hat. X hat is along the x direction, in this case the horizontal direction, and y hat is the vertical direction, and we're choosing up to be positive. So in this case, it's just the magnitude with a negative sign times the unit vector. So it always points down no matter how the object is moving. Gravity is just pulling the object down. It's a long-range force. It doesn't require contact, and the agent is the Earth itself. Okay, the second force on the list is the spring force. We denote as F subscript spring, SP, and this is one of the most basic contact forces. A spring can either push or pull. Remember, gravity was always pulling. A spring can push or pull depending on whether it's compressed or stretched. The magnitude of the spring force is given by K times delta L. This K is the spring constant. It's just a number that characterizes the stiffness of the spring. So each material has its own spring constant, and this is usually a given. So you look at a spring, if it's hard to compress or stretch, this has a high value of spring constant. Or if it is relatively easy to stretch or compress, then the spring constant is small. So this measures stiffness. Delta L is how much the spring is compressed or stretched. I should put this in absolute value notation because I'm talking about the magnitude. So delta L is compression or stretching. Okay, this is easy to understand if we draw a picture. So let's say we have the spring here, uncompressed, unstretched. This is just the natural length of the spring. Let's say it's L naught, or let's call it L initial, just to be consistent with the notation we used for velocities and stuff. Then let's compress the spring. So now it is at a length L final. This is delta L here. So delta L, it can also represent a spring that is stretched. So this could have been the L final instead. And in that case, measured from the relative position, that would have been delta L, depending on the situation. So it can represent a compression or a stretch. And depending on how much you stretch the spring or compress it, there is a restoring force that the spring exerts, trying to restore itself to the natural configuration. So spring force is a restoring force. So direction, the spring force is a restoring force. So if the spring was compressed, it tries to push the object away. And if the spring was stretched, it tries to pull the object back to the equilibrium position. So its direction depends on the situation. For example, if we let's in each of these cases attach an object to the spring. Let's attach a box here, and the box there. In the first case, where the object is at equilibrium, there is no spring force. The spring just doesn't exert any force. It's at equilibrium. It's fine. In the second case, the spring is pushing the object away. So the spring force is pointing outwards. And in the second case, where the spring is stretched, the spring is trying to pull the object back. So the spring force can change direction depending on the situation, is all I'm trying to say. Good. And then one final remark is that a spring doesn't always have to be a metal coil that can be stretched or compressed. This is only one type of spring. Basically, everything can be a spring. If you take a ruler and you bend this ruler, it tries to get back to its equilibrium position. So that's also a spring. Even a piece of wood, if you try to bend it, it also tries to get back to its equilibrium position. What makes these objects different is the stiffness or the spring constant. So pretty much everything in the world can be treated as a spring depending on the spring constant. Okay, good. The third force on the list is tension force. We denote the tension force by capital T. Small t is reserved for time, so capital T is the tension force. It's always a pull. It can never be a push. The tension force is exerted by a rope. So if you try to push something with a rope, the rope goes slack and there is no force. So it's a pulling force. The agent is the rope, and it's a contact force. So it exerts a contact force with the object it's in contact with. Let's say there is a box, and this box is attached to a string, and it's on a ground. So it's being pulled by a tension force T. This is a box. This is a rope. It exerts a tension force T, a pulling force. Again, the agent is the rope or the string. No formula for tension. So tension is one of the forces that, well, it adjusts itself to the situation. It has a range, and then up to some point, it just cannot sustain the other forces, and the rope goes slack. But there is no specific formula for the tension. That's all we have to say about tension. Then there is the normal force. We denote it by small n. Some textbooks prefer to use uppercase N, but I reserve that for the units of forces. So the unit of force is a Newton, and Newton is a capital N. So I reserve that to the units. Or sometimes it's denoted as F sub N, but I prefer to use this lowercase n. The agent is a surface. The normal force is always exerted by a surface on an object in contact with that surface. For example, let's say we have a table or just the ground, and we have again, our favorite example, a box on the ground. Let's make it a table, not the ground, so not to confuse it with gravity. So a table. The normal force is exerted on the box perpendicular to the surface. It is basically the force that prevents the object from going through the surface. The word normal in this context doesn't mean natural. So it's not a natural force. All forces are natural. There is no made-up forces. So it's not the natural force, it's a normal force. And normal in this case just means perpendicular. It's the word used in mathematics to denote that something is perpendicular to another. So normal here means perpendicular. So it's always perpendicular to the surface of contact. So if the surface tilts, if you have the box along a ramp, for example, and this ramp has some angle theta, and the box is sliding, the surface still exerts a normal force, and the normal force is still perpendicular to the surface. It is not always vertical, but it's always perpendicular to the surface of contact. Okay, if you tilt the surface, the force tilts with it. And again, the normal force doesn't have a formula as well. Okay. Then we have friction. Friction is denoted by a lowercase f, and it's a resistive force. It's a force that opposes or resists relative motion. The word relative here is very important because it doesn't just resist motion in general, it resists relative motion. For example, if you have two objects on top of one another, and these two objects are moving together, then the relative motion is zero. One object is not moving relative to the other. Both are moving relative to the underneath surface, which is like a table or the ground, but they're not moving with respect to one another. So this will come up in examples where we have to figure out what is the direction of relative motion to figure out what the direction of friction is. We have two types of friction. Static friction. From its name, this is the friction when there is no relative motion yet. Things are at rest with respect to one another. It's denoted by a subscript S for static. And the second type is kinetic friction. And there is relative motion. It's denoted by F sub K for kinetic. The agent that exerts the friction force is also a surface. So yes, a surface will in general exert two different forces. It will exert a normal force perpendicular to the surface, and it will exert a friction force. In this case, friction force is parallel to the surface. So let's write that down. Friction is exerted by a surface, this is the agent, on an object in contact with it, it is always parallel to the surface of contact. So if we take the two examples we have here, or let's take this particular one for the object tilted, and there was a normal force that's still there. But let's say the object was moving down. So relative motion is down with respect to the surface. Then friction would be going this way. And if there was motion, then this is kinetic friction. It is parallel to the surface. And it's always perpendicular to the normal force. Okay, so far so good. This is a discussion on the on the directions, no magnitudes yet. Friction opposes relative motion. We have two types. We have static and kinetic frictions. The agent is always a surface in contact with the object, and the direction is always parallel to the surface. Then what is the magnitude? Friction is a little bit tricky because sometimes it does have a magnitude determined by a formula, and sometimes it doesn't. So the easier one is kinetic friction. So kinetic friction always have a magnitude. Kinetic friction, always have a magnitude formula. F sub k, the magnitude is equal to mu sub k. This mu is the Greek letter sub k. This is just to denote the kinetic part, times the magnitude of the normal force. I can just write this simply as F sub k equals mu k n. If I don't want to write the vectors and absolute values, by just understanding that this is a magnitude notation, if I don't put the vectors. This Greek letter mu, this is the coefficient of kinetic friction. This is not the force of friction itself. It is a coefficient. It measures how rough the surface is. So if mu is 0, there is no friction. No matter how hard the normal force is, there is no friction. If the surface is rough, then this coefficient of friction will be larger because more normal force is associated with more and more friction. So it's an experimental parameter to determine the roughness of the surface. Okay. A common mistake is that when students are given the coefficient of friction in a problem, they use it as the force of friction, and this is not correct. It is only a ratio between the force of friction and the normal force. So don't use it as the force of friction itself, and it is dimensionless. It doesn't have any units, just a number. This is kinetic friction. It always have this formula, but static friction doesn't always have this formula. So static friction is tricky. Static friction can vary all the way from 0 to a maximum value that we denote Fs max. Let's say there was a box sitting on a table, and then you try to move this box. Before you exert any force, there was no friction. Then you try to pull the box. It resists a little bit. You try to pull the box even more. It resists more, so the friction force increases. And at some point, the box gives up and moves. So during this process, the static friction increases until it gets to a maximum. Once it gets to a maximum, the maximum value of it is given by the formula mu sub s times n. It's the coefficient of static friction, and n is the normal force. Before it reaches this maximum value, there is no formula for static friction. You have to figure it out using other forces in the problem and equilibrium properties and stuff, using Newton's laws and balancing forces. But once it reaches this maximum value, this is the formula it's given with. Okay. We always have the coefficient of static friction is bigger than coefficient of kinetic friction. And therefore, because the normal force is the same in both cases, you have the static friction, or the maximum static friction, is always bigger than the kinetic friction. It takes more force to get the object to move than to resist its motion. Okay. The final force is drag. Before we get to drag, is there any questions on friction? Because that was a little intense. Honestly, we're not going to use drag that much, but it's just for completeness. Let us discuss it. Drag force. It is a resistive force experienced by an object moving through a fluid. It's similar to friction, but it's a little bit different because now the friction is from the whole fluid, not just from a contact surface. So we denote that by F sub D, or sometimes just uppercase D, but I prefer F sub D. And by fluid here, we don't just mean liquid. Air is a fluid. An object falling down, if it's not a free fall, if it's not under gravity alone, if air resistance is not ignored, air resistance is a kind of drag force. If, for example, we have a leaf falling down from a tree, air resistance cannot be ignored on a leaf. It has a big surface area, and you can pretty much see it. If a leaf falls from a tree, it takes much longer to get to the ground than if a ball falls from a tree or if a fruit falls from a tree. So drag impedes its motion. So if we draw the leaf as a point, then there is the drag force upwards trying to resist its motion. There is also gravity pulling it down, but we just take one force at a time here. But then again, we always ignore air resistance in this class, so it's just useful to know that there is such a force, and we're not going to see it again. Okay. I want to mention again that in our discussion of all these forces, we didn't mention Newton's second law. The overview in the beginning, when we mentioned Newton's second law and stuff, that was an overview for what to come next. But when we introduced the forces, we didn't mention Newton's second law in their definitions. So drag, friction, tension, spring, gravity, all of these didn't involve Newton's second law at all. These are defined independent of Newton's second law. Okay, even if nature didn't follow Newton's second law, these will still be the forces, and then there will be some other law to relate them to one another. But essentially what we're considering is just the cause without the effect yet. Okay, only the cause. Next time we're going to discuss the effect, but now it was just the cause. Just have two more sections before we take a break. We have free body diagrams and combining forces, and these are crucially important. After that, we're gonna work on a worksheet just to get these ideas together, but just bear with me for like 20 more minutes. Free body diagrams. This is very important. Every problem in dynamics you solve, you must start it with a free body diagram. Every object acted on by forces, to figure out what these forces do, what the net force is, how they combine, what acceleration do they cause, you must start with a free body diagram. So it's a skill you need to master. So please pay attention to how to construct a free body diagram. So a free body diagram is a tool. It is useful because it assembles all the information about forces that act on an object into a single diagram. Let's go step by step on how to construct it. So first, construct a coordinate system. Okay, construct a coordinate system with two axes, x and y, as usual, just a Cartesian coordinate system. The most practical orientation is to align one of the axes with the acceleration or with the direction of motion. This is practical because acceleration is a vector. So when you align the direction of motion with just one axis, you know that the other axis doesn't have acceleration, so you can just treat it as a balancing between different forces. And it becomes mathematically much easier. But if you put your coordinates generically, then you have to deal with vector decomposition and all the angles and trigonometry and all that stuff, and it complicates the problem for no good reason. So it's smart to align one of the axes with the direction of motion. For example, if the motion is horizontal, let the x-axis be the horizontal and the y-axis be the vertical. If the motion is along an inclined plane, tilt your coordinate axis. So for example, if you have, let's see, if you have a tilted plane with an angle theta here, and you have a box here moving down, so this would be the direction of motion, then you are absolutely allowed to put your axes like this. This is the x-axis, and this is the y-axis. They're two perpendicular axes. Yes, they are not horizontal and vertical, but they're aligned with the motion and perpendicular to the motion, so that makes it much easier to solve. Coordinate systems are constructed, they are not physical, they are not relevant to what happens in nature. We just choose them for convenience. So you're absolutely allowed to tilt your coordinate systems whenever it's convenient. Okay. So that's constructing coordinate system. The next step is to represent the object as a point at the origin. If it was a box, then put it a point. If it was a car, again, a point. Anything complicated, we just represent it abstractly by a point. Third and most important step, draw each vector acting on the object as a vector. And this vector is located at the particle, so the tail of the vector, and then extend the vector so that it points along the direction of the force. Finally, the length should be roughly proportional to the magnitude of the corresponding force. Okay. So let's look at that example up here for the object moving at a plane. Let's apply to it what we just said. So we did the first step, which is constructing the coordinate system, right? So the object is a point at the origin. So here is the object. It's a point at the origin. And draw each force acting on the object as a vector. We know that there are three forces acting on the object. First is the force of gravity, its weight, that's always there. This is vertical, this is vertically downwards. So this is F sub G. And its tail is located at the object, and it's extended so that it points in the direction of the force. There is also the normal force, and this is perpendicular to the surface of contact. And there is friction. If the object is moving down, then there is friction parallel to the surface opposing the relative motion. So this is friction, and it's kinetic because there is motion. That's it. That's the free body diagram of the object. It's a point. We have the axes and we have the forces. We have all the labels. So the final step, which I did without writing down, was label each force. Okay. If there is more than one force of the same type, distinguish them by different labels. If you have two tensions, for example, don't use the same symbol. Use T1 and T2 or TA and TB, but just have different labels. So let me write that as label each force uniquely. Okay, this is best explained with examples because this is, yes, the general procedure, but it becomes much easier when you look at different examples. So let's take an example. We have the first example says, an elevator suspended by a cable speeds up as it moves upwards from the ground floor. Draw a free body diagram of the elevator. So motion is up, so I will construct my coordinate system to be like this. So up, y, and so it doesn't need to be tilted because motion is up anyway. I will put the elevator as a point at the origin. And then the forces are, well, there is always the weight of the elevator, Fg. And it is suspended by a cable. That means there is a tension from the cable pulling it up. It speeds up as it moves upwards. So the tension force is upwards along the y direction, and it's denoted T. That's it. That's the free body diagram for the elevator. That's really it, nothing more. Another example, it says a rope pulls a skier up a snow-covered hill at a constant speed. Draw a free body diagram of the skier. Okay, in this case, the hill is tilted a little bit, so the coordinate system is going to be tilted as well, so it's tilted at an angle theta. The x and y coordinates, I can tilt them accordingly to be like this, x and y. And then the skier is a point at the origin. Okay. And I want to write down the forces acting on the skier. There is the weight. The weight always exists. So it's Fg. There is the, oh, I didn't want to have the axes that thick. So let me I want them to be in the background. Okay. Then there is the tension from the rope pulling along the ramp. So this is T. And then there is, from the surface itself, there is friction and there is a normal force. The normal force is always perpendicular to the surface of contact. So it is pointing here along the y direction in this case. And because the skier is moving up, the friction is pointing down. And if it's moving, then it's kinetic friction. These are all the forces acting on the skier. 4 forces in this case. Okay? Good. We're almost there. There is one final thing we need to mention, and then we're gonna take a break. Final thing is combining forces. This is nothing you haven't seen before in vectors. See, what we are doing here is all vector representation, vector addition, vector decomposition. We're just giving these vectors a physical nature. We're just dealing with them as forces now, but they're still vectors. They're still the same rules apply, the same addition rules apply, the same head-to-tail rule, the same parallelogram rule, the same vector decomposition rules. All of these apply. But let's, for example, look at this skier example. We have 4 forces, and all of these forces act in different directions with different magnitudes. At the end of the day, the skier will just move in a particular direction with a particular acceleration. So it just responds to a net force, not to all of these individual forces. It responds to a net force. So we need a way to calculate the net force. And this is what later enters Newton's second law when we say force causes acceleration. It really is the net force that causes acceleration. So the net force is just the sum of all forces that exist in a problem. So if we have forces F1, F2, F3, etc., you just add them all vectorially. The important part is adding them vectorially. You don't just add magnitudes. In one dimension, this would be just taking care of the signs of the quantities, but in more than one dimensions, that would mean you have to have an x component and a y component. So this would mean x component, you would have f net in the x direction. This is the x component, is f1x plus f2x plus f3x plus dot dot dot. And the same thing for y component. You just decompose your vector into x and y components in exactly the same way we did with kinematic quantities. This is the algebraic way, but there is also the pictorial way. If you have, for example, 2 forces pulling a box, let's say this is the box and this is F1 and this is F2, then you can also do it pictorially. Here, the parallelogram method is the most useful because all the forces begin at the same point, which is the object itself. The tail is at the same point. So you use the parallelogram method where you have them draw parallels like this. And then the diagonal is the net force. So this force would be F net. Okay, so you have 2 approaches. This is a graphical picture, and this is algebraic. Later, Newton's second law says that F net equals ma. So it's this net force that is the sum of all forces that goes to the left-hand side of Newton's second law. And this net force comes from all the forces we discussed in this lecture: tension, friction, normal force, gravity, spring, all of these forces, they only enter the left-hand side. Next time, we're going to see the right-hand side and how it responds.